Hello and welcome to 9.2. So I hope that you had lots of fun with 9.1, which was the basic SOHCAHTOA trigonometry. And in 9.2, we're going to do a little bit more looking at angle measures, and we're actually looking at angle measures kind of on a circle, even though trigonometry has to do with triangles, and you'll see why, especially as we get into the unit circle, which is the mini lesson in between 9.2 and 9.3. And then as we get into 9.3, you'll see why this section is so important. So the first thing that we want to do is talk about two different ways that we can measure an angle. One way is a degree. You guys are already used to degrees. From geometry, you know the definition maybe, that a degree is 1/180th of a straight angle. So if I make an angle where the rays are pointing in opposite directions, that's a straight angle. And if I split that into 180 equivalent angles, then that would be considered 1 degree right there. It would be a 180th of a straight angle. A radian you might be less familiar with, or you maybe have never heard of a radian. A radian is just another way to measure an angle. Kind of like if we were measuring length, we could measure it in feet, or we could measure it in meters. They're two different systems. They don't really have anything to do with each other, although they both measure length, and we can convert from feet to meters or from meters to feet. Degrees and radians act similarly. So the definition of a radian is the angle swept out. If I take a circle and I make the radius and the arc length equivalent. So here's the radius of my circle. If I draw an equivalent length, that looks about right. And this arc length is curved, right? So we're not calculating the straight distance length. That's a curved length. If those two lengths are equal, then the angle that's swept out here, that would be 1 radian. So which is bigger, a degree or a radian? Yes, good job. A radian is way bigger than a degree. And we'll see what that conversion is in just a little bit. So those are our two different forms that we have for evaluating angles. And here's a little bit more of angles and some vocabulary as well. So a standard position of an angle, if I draw some X and Y axes, standard position of an angle would be counterclockwise from the positive X axis. So the angle has what's called an initial side right here. Initial just means beginning, right? So that would be the initial side of the angle. And then the other ray that makes up the angle is called the terminal side, just like an airport terminal, right? It's a stopping place. So that would be the terminal side of the angle. And when we measure the angle, it goes from the initial side to the terminal side, counterclockwise. In geometry, you may have talked about the size of the angle, but never actually given it the direction of counterclockwise or clockwise. So standard position is counterclockwise from the positive x-axis. And we'll be working with angles in standard position only this section. We also have vocabulary word of coterminal angles. Coterminal, think about the vocabulary. The prefix co means together or with, and terminal, we just talked about, that would be where they end, right? So these would be angles that end in the same place. For instance, I could have, let's just say that this is a 20-degree angle right here. And then to find a coterminal angle, I could say, okay, well, let's find an angle that would land in the same spot as that. It has to start in the same spot as well. It has to still be in standard position. So how can I start here and end there, but have a different angle? Well, I can go all the way around the circle and then land at the same spot. So I'm still starting on the positive x-axis and I'm still landing at the same spot, but now this angle would be 360 degrees to go all the way around, plus the other 20. So 20 degrees and 380 degrees would be coterminal angles of each other. I also, if I wanted to find another coterminal angle, I could also go clockwise. And we had said, well, the standard position is counterclockwise. Turns out if you go clockwise, then that's going to count as a negative angle. So the angle that I have marked in black would be an angle of negative 340 degrees. And that would also be coterminal with 20 degrees. So coterminal means they end at the same spot, right? That's all you're going to get for that. And then I have two formulas for you. There's a formula for the length of an arc and for the area of a sector, which is a pie piece in a circle. So you may have, again, seen these in geometry. It turns out that arc length is, and we use a cursive letter L for that, arc length is r times theta, as long as theta is in radians. Or if theta is not in radians, then L, you can find the arc length by thinking about the proportion of the length of the entire circle, which is the circumference. So you can think of the arc length as a proportion of the circumference. For the area of a sector, the same thing. So if theta is measured in radians, then that is very helpful for us. And we have this formula for the area of a sector, that the area of the sector is going to equal 1/2 theta r squared. That's if theta is in radians. Then we can just use the formula. However, if theta is in degrees, which is what you're more familiar with working, then instead we can think of it as a proportion instead of using the formula. So you've got the two choices, right? One or the other. If theta is in degrees, you can think of it as the proportion of the area of a whole circle. So you can think of it as the proportion of pi r squared, which you know to be the formula for the area of an entire circle. Okay. So let's do some examples. Draw an angle of 150 degrees in standard position and then find a positive and negative coterminal angle. Go ahead and try this on your own. So pause the video and then we'll go over it in 3, 2, 1. All right, here you go for you to check your work. So 150 degrees is going to land solidly in quadrant 2. It's going to be 30 degrees away from hitting the x-axis, right, to get to 180. And then make sure that you would have the arrow on your angle that you are indicating that that's going in the counterclockwise direction. So then to find the coterminal angles, we simply can go from there around, continue around a whole nother circle, which would be adding 360, and we'd end up with 510 degrees. Or we can start on the positive x-axis and go clockwise, which is a negative angle, and get negative 210 degrees. The size of the angle is 210, but the negative just indicates the direction that I'm going in a clockwise manner. We can do this also for radians. So for radians, it may be helpful to kind of have an idea in our head about where some radian measures are located. And so to do that, we're gonna look a little bit at the definition of a radian and look at a circle. And you'll see a little bit more of this when we fill out our unit circle, which is the lesson right after this. So we had said that when you let the radius be equivalent to the arc length, then that is sweeping out 1 radian. And degree symbols are the marker of a degree angle, but radians don't have a marker, so you would have to write the letters RAD after them as a symbol, unless they happen to be a multiple of pi, which a lot of them are. So let's go ahead and keep sweeping out so we can kind of see how many radians are fitting into a circle. So then this would be another radian right there. So together that would be 2 radians, and let's sweep another one out. And this would be about 1 radian. And so you'll see that we get 3 radians in before I get to the negative side of the x-axis, but they don't exactly fit. It would be so nice if they exactly fit, but there's this little leftover part. Turns out that that leftover part is 0.1415926, etc. of a radian. It's that fraction of a radian that's left. And so if you add these up, I hope that you are as amazed as you should be, that it turns out that we get pi radians in half of a circle. Are you amazed? Okay, just stopping to appreciate that. So now we can say, well, then we know that this is 180 degrees over here in standard position, right? That would be 180 degrees. And so that also means that we also said that that was equivalent to pi radians. And so some of the important angles that we'll be looking at are all the multiples of 30 degrees and all the multiples of 45 degrees. So I can go through and I can mark some important multiples. I might not be marking them all, but they're on page 472 of your textbook if you'd like to find them. So if this is 180, then 90 would be up here and 0 would be over here. And if I break that 90 degrees in half, I'd land at 45. And so if I count by 45s, I would have 45, 90, 135, 180, add another 45 over here, I get to 225. And then this would be 270, and then 315, and 360. Those are all pretty important. Now 0 and 360 are coterminal, right? Because they end at the same spot. So you can label both of them if you want, but you don't need to. I could continue going around counting by 45s if I want, but I don't want to, and neither do you. We just want to stick with these. So let's do the same thing with radians to kind of get a feel for your radian measurements. So if pi radians is half of the circle, then if I split that in half, I get a half of a pi, right? A half pi, or pi over 2. Now I want you to resist the urge to think about the circle as an actual pie that you would eat, because turns out what I just called a half of a pie is not actually half of you eating a pie, right? It's actually a quarter of a pie that you would eat. And so please don't get confused on that. Pi is just half of the circle, and so this would be pi over 2. And so if I split that in half, then that would mean that pi over 4 is the equivalent of 45 degrees. So I can go around and count by quarter pies. So pi over 4, this would be 2 pi over 4. This would be 3 pi over 4, and then 4 pi over 4, 5 pi over 4, 6 pi over 4, which reduces to 3 pi halves, 7 pi over 4, and then 8 pi over 4, which would be 2 pi. So we had said degree symbols, right? You would always want to write the degree symbol on the degree measurements. For radian measurements, you either have to write the letters RAD, or if they happen to be multiples of pi, like a lot of the angles we're going to be looking at, then you don't have to write a unit at all for it, because if you can see pi in the angle, then it's assumed that that's going to be a radian. So those are the multiples of 45. We can also look at the multiples of 30, so 30 degrees, 60 degrees, etc. I'm not going to do all of those for you because they're on page 472 of your textbook, and we're going to be looking at those a little bit more in the next lesson anyways. But I do suggest that you turn to page 472 and that you would copy all these down on a piece of paper somewhere. So we have a couple things left. We need to be able to convert back and forth between the sizes of the, between the measurements of the angles. So if I have 7 pi fourths and I want to convert that to degree measurement, if I recognize that that is on the circle that I just drew on the last page, then no work needs to be done. I can simply say, hey, look, there it is. That was 7 pi over 4, and that turns out is equivalent to 315 degrees. And that's all I would need to do, no work necessary. However, if it's 3 pi tenths or something like that, that's not one of the special measures that's on the unit circle or on that circle that we drew. And so I would need to work out a conversion factor. Just like when we were doing dimensional analysis and saying that 5,280 feet is equivalent to 1 mile, or 60 seconds is equivalent to 1 minute. And so if we go back to this picture, the easiest equivalence that I can use is that pi radians equals 180 degrees. So if this is a radian measure, right, then to convert it to, and I can go ahead and give it the unit of that those are radians. If I want to convert it to degrees, then I would have to say that pi radians equals 180 degrees. So I'm going to multiply by 180 over pi. That's an equivalence factor, right? So it changes the number, but it also just changes the symbol. So radians goes away, and now the unit I have left would be degrees. To simplify this, I don't need a calculator because I can say that, well, also the pi divided by the pi would go away, and the zeros would go away. And so I get 3 times 18, which is 54. And so I get that that's going to be that 3 pi tenths radians is the same as 54 degrees. Similarly, if I give you degrees, then you need to be able to convert that back to radians. So if it's something like the bottom example, that's 180 degrees, and you already know that 180 degrees is pi radians, then that's no work necessary. But if it's 15 degrees or something like that, then we would need to, again, find the equivalence factor to multiply by. So if that's 15 degrees, if I want degrees to cancel out, then I need the degrees to go on the bottom. And so I'm going to say 180 degrees is equivalent to pi radians, and then simplify what I can, right? So the degree units would go away, and 15 180ths I can reduce. So you can reduce those by dividing each of them by 5. And if you do, then you would get that this is 3 pi over 36. And then you'll say, oh, look, and they also divide by 3. So then we end up with pi over 12. Now, if you want to do that in your calculator, I'm okay with that. Hopefully you know how to do that by using the subtract button. So you could just type 15 180ths and hit enter, and it'll give you that decimal equivalent. And then you could hit math, enter, enter, which is going to convert that to a fraction of 1/12 for you. And then you just have to remember to tag the pi on. So that's converting. And last but not least, arc length and sector area. So using our picture, I can see that my angle is measured in degrees. So instead of using the formulas, I'm going to want to just think of these as proportions of the circumference or proportions of the area. So the arc length that I want, first off, let's find the circumference of the circle. The circumference of the circle I know is, the formula is 2 pi r. And so this would be 2 pi times 5, which is 10 pi. That would be the circumference of the circle. So the arc length that I have marked out there in purple is 125 out of 360, because there's 360 degrees in the whole circle, 125 3/60ths of the entire circumference. So that's the 125 3/60ths of 10 pi. And then let's go ahead and put that in our calculator to get a decimal approximation for that. So 125 3/60ths times 10 pi. And I get 10.908 approximately. And because I gave you the units of feet on the radius, we would also want to mark that that arc length is also in feet. So that's arc length. For sector area, again, because we have degrees, we could convert it to radians and then use the formula I gave you. So you're welcome to do that. But because I already have degrees, let's just think of it as a fraction of the whole area. So the area of the whole circle, and this is not a zero, this is a circle, a picture of a circle. The area of the circle would be pi r squared, which is 25 pi. And so again, if I'm looking at just the sector swept out by the 125 degree angle, then I can say that the area of the sector, that should look like a pie piece, the area of the sector is going to be 125 out of 360. That's the fraction of the whole area I have. So it would be 125 3/60ths of 25 pi. And then again, just stick that in your calculator. So 125 3/60ths times 25 pi. And we get 27.271. And this is area, so the unit for that would be square feet or feet squared, right? That would be the area of the sector. So I hope that sets you up for your homework. I think that you'll be doing fine. Also, just in case you may not know where the pi button is on your calculator, it's over here on the right-hand side. It's seconds and then the caret, like the exponent symbol. So second and then that'll bring you up a pi button, and that gives you lots of decimal places of pi so that you're not going to put in 3.14, which is such a rudimentary approximation. So have fun with your 9.2 homework and come to office hours if you have any questions.